I next have the extreme pleasure to introduce Dr. Frances Arnold, who will speak about the nature of innovation and diversity innovation in nature. Her research at Caltech is on directed evolution and protein engineering. Dr. Arnold's laboratory has developed methods of laboratory evolution and structure-guided recombination that is used widely in industry and in basic science to engineer proteins with new and interesting properties. I should note, of the 6,000 plus members of the National Academy of Engineering, the National Academy of Sciences, and the Institute of Medicine together, she is one of 14 who is a member of all three academies. Frances, the floor is yours.
Happy 50th to the National Academy. I really want to say that because I really love being an engineer. In fact, I have a lot of different fun jobs, but one of my fun jobs recently has been to be a judge for the new Queen Elizabeth Prize in Engineering. And the QEP folks recently engaged the engineering community online to vote for the greatest engineer of all time. The greatest engineer of all time. I mean, think about that. That could be Archimedes or Leonardo da Vinci, Thomas Edison. But I didn't think about it very long because I knew the answer right away. For me, there's just one answer, and that is nature. Nature is truly the greatest engineer of all time because you only need to look around you. I think I have some pretty pictures here. You only need to look around you to see the most marvelous feats of engineering. Nature extracts materials, energy from the environment, and converts it, seemingly easily, to self-replicating, self-repairing, adaptable, mobile machines that sometimes even think, sometimes not. But you've got 4 billion years of innovation, of exploration, trial and error, Darwinian processes that gave rise to a truly stunning array of solutions to a very important problem of being alive. And not just being alive, but enduring for billions of years. Nature's engineering solutions are constructed from an equally stunning array of molecular machines. These are the things I really enjoy working with. And these machines do all the work. They catalyze the reactions, they carry the cargoes, they copy the DNA, the information. They convert one form of energy into motion. And they are really the functional parts of life. We heard a little bit from Eric about how interconnectedness is important. Well, let me point out that this diverse set of solutions to the problem of being alive are wonderfully interconnected. Do you know that you have on you and in you 100 trillion cells, microbes, 10 times as many cells as you have human cells, without which you would not thrive. You wouldn't even survive. They control your moods, your immune system, your very survival. In fact, you are their planet, and they can nurture it or they can harm it. And if you upset their balance, you will pay the price of that. In fact, for me, life is by far the biggest and most creative of the internets. It's the internet of living things, and it's robust, decentralized, organic, adaptable, and it's constantly changing and responding to new challenges. It invents new solutions to problems, and it builds upon existing ones. It evolves. As we learn more about life, all these advances that Erica alluded to, we're astounded, truly astounded at the clever solutions that nature has devised to solving specific individual problems on the road to being alive. that are not unlike many of the problems we human nodes of this internet face in our bid to survive as part of it. In fact, I think that human engineers have a lot to learn from biological systems. And for one thing, we could harness some of these brilliant designs for our own purposes. These microbes, for example, that sit in and on you are marvelous, brilliant chemists. They are particularly good at converting food into a lot more microbes. That's what they have been optimized by Darwinian evolution to do. But I'm one of a number of bioengineers who think that we could reprogram these microbes to perhaps slow down the process of making more microbes and turn some of this marvelous chemistry into solutions to making new chemicals, to being essentially the chemical factories of the future. So maybe we could do that. Perhaps we could live more sustainably on our planet, in balance with the other life we do have to share it with, by getting these little microbial factories to convert their natural foods, waste materials, plants, even energy directly from the sun and carbon dioxide from the atmosphere, into those fuels and chemicals that we need to survive on this planet, rather than pumping it all out of the ground and dumping that into the atmosphere. Others in my field look to reprogramming biology in order to feed this growing population. And as you know, this is especially important in an era of rapidly changing climate. We will have to learn how to adapt to that, and reprogramming biology will have to be a key part of that solution. But if we could engineer crops to resist the heat and drought stresses that we expect to face soon, or create more nutrient-rich foods, someday maybe even replace food animals. I know this sounds terrible to some of you, but it would be nice to replace food animals with high-quality products that we could actually make in a reactor. We'll also use biology, and specifically reprogrammed biology, to move into intellectual frontiers in science and in technology, such as understanding and manipulating the brain, something that, of course, my field, folks in my field and other engineering disciplines are already doing, using engineered cells, engineered neurons that we can control, for example, with light and activate, or with chemical signals, or engineering the sensor and activating proteins that can help us understand the molecular basis of disease. Now, all of this biology, all of these functions are written in a simple 4-letter code. All the information storage and programming language of a cell is in this simple code that we can translate into proteins, but we really can't read it. We're starting to learn pretty well. Or as Eric Lander said in his 7-word abstract for his Ig Nobel Prize about the human genome, bought the book, hard to read. I often think about what my 7-word abstract would be. That's an interesting goal. But you think about this, DNA whose structure was only determined about 60 years ago, in our lifetimes. But that marked the beginning of a technological revolution that has put a completely new engineering discipline out there. This is a whole new field, a whole new set of opportunities for engineering. And it spawned this technological revolution that was spawned by these discoveries of molecular biology and recombinant DNA is moving so quickly that some of us may well live to see a new origin of life in the 21st century, life being created from non-living material. This hasn't happened yet, but you might have seen these headlines from 2010 heralding this new era of synthetic biology. Scientists at the Venter Institute synthesized from chemicals the entire 1 million base pair genome of a simple cell. And when they put that synthetic DNA back into a cell whose DNA had been removed, that cell rebooted. It read the DNA as if it were its own, and it started following the program in that cell, and it grew and divided. But the problem is, not that we have this technological capability. What we don't know how to do is how to compose that. Those scientists took all the beautiful music from nature. That genome composition was the product of evolution. And we don't know how to write like this. We're just learning how to hold the pencil. We don't know what is the code for converting sunlight and carbon dioxide into liquid fuel, into gasoline substitutes. We don't know that. We don't know the code for a drought and stress-tolerant plant. And we certainly don't know the code for a longer, healthier life. Right now, we just grab these bits and pieces from the natural world and string them together, which is kind of like writing Moby Dick by pulling paragraphs off of Google. You don't get great literature that way. But humans we've been modifying the biological world for a very long time. We've been rewriting DNA for thousands of years. We've used artificial selection to do it. Without even knowing what DNA is, we've been modifying it in everything from corn to carrier pigeons, lab rats, racehorses. We've created biological entities that you would not find in the natural world, but are useful to us. And thus, evolution, this simple algorithm of mutation and selection, can be used for forward engineering. We've been doing this. Until now, of course, the mechanisms for breeding have been somewhat limited, right? The natural mechanisms for breeding are monkeys with monkeys, worms with worms, and never the two shall meet. But remember, that's all changed. I can synthesize any DNA I want. In the test tube, I can mix together DNA from monkeys and worms. I can make any number of mutations I want. Of course, so now I have my sticky fingers on this biological evolutionary wheel, and I have to learn what the rules for driving are. I have no clue. We're at the very, very beginning here. So it's a blessing and a curse, and I have to figure out what those rules are. Sex with 3, 33, fungi with foxes, fish. How many new mutations do I dial in, and what can I expect to create by this process, right? What can I hope to get out of it? Can I create new molecular machines that are useful? Yes, I can do that, and we have, in my field, done that. Novelty's fun, right? But can we create something that's useful in this new molecular breeding process? And this is not science fiction. It's really not science fiction. By directing the evolution of microbes and their component protein parts, my laboratory and those of many others who practice these methods in synthetic biology and bioengineering have made everything from better laundry detergents to gasoline substitutes. Now, perhaps you don't play with DNA like I do, but directed evolution, the ability to evolve DNA that encodes useful things in the laboratory, has lots of parallels with some of the things that you do. Many of you in this room have made major contributions that have enabled us to live longer, happier lives. Those are your engineering contributions. And we, as you've heard, we're going to rely on having yet more such contributions, new engineering contributions, to provide those same benefits to future generations. What can we learn from evolution in this process? Evolution is innovative, right? What can we learn from this? Well, what I've learned is that technology evolves, and you can just see this, very much like DNA evolves. We create solutions to problems, not by starting from scratch. When you make a better hammer, you don't start with a rock. We don't start from scratch, but we start from partial solutions that we can find around us. We build upon those solutions, mostly incrementally, a little uphill walk like evolution does. And those that serve us well get propagated, those that don't go extinct. And they can diverge into a breathtaking diversity of specialized solutions, not unlike what we've done with the directed evolution of things like dogs. Look at all the dogs we humans have created through this specialization and incremental change. And it's not unlike what I do in the laboratory, creating new proteins by directing their evolution. But you might be asking, oh, right, evolution is evolution, but what about true innovation? What about true invention? How do real innovations come about? Well, we know that evolution also does real innovations. Sometimes invention comes about by assigning a new purpose to some old invention. And this happens all the time in nature. Nature discovers, for example, that an existing enzyme catalyzes a reaction, just happens to catalyze a reaction that degrades a compound that we humans have put on this planet for only 50 years. But thank goodness, somebody out there in this vast internet of living things has a catalyst that might be able to degrade that, even at some low level. But that capability gets grabbed by nature and grabbed by evolution and improved over multiple generations until a whole new capability arises. This happens in invention. Think about recognizing that a virus surface could template inorganic materials, nanoparticles of inorganic materials. And those particles could grow into nanowires, which could be used to assemble a high-efficiency battery. That's repurposing a virus. Or they could form a nanowire catalyst that can couple two atoms of methane to make ethylene efficiently, so that we could use vast methane resources to make fuels and chemicals. A human being can make that connection if she has the varied experiences with biology on one hand and materials engineering on the other, like Angela Belcher of MIT, who won last year's Lemelson Prize. And Siluria, the company that she co-founded with her students, highly innovative, raised tens of millions of dollars to develop this technology, a technology built first on the backs of viruses. Now, most inventions come about by recombining known technologies. And if you have a diversity of known technologies, these are the building blocks from which new inventions can be built, you can have interesting recombinations. And of course, most recombinations are useless. If you randomly recombine technologies, most are useless, but some are truly brilliant. How can we nurture and promote such innovations? Well, we can look to nature for some guidance there, because what we know from the natural world and the ability to adapt to rapidly changing environments is that diversity is critical, right? You have to have a diverse set of parts to create something new, or it helps if you're going to be there first. So for example, if you have a diverse set of technologies, which is your genetic material, these are the genes from which new solutions to problems get assembled. You don't have to build these building blocks from scratch. You can recombine them in useful ways, and you don't have to reinvent those. And the greater the selection of any given part, right? You may need a particular seal, and if you don't want to have to reinvent it, it's nice to be able to go to a catalog and get exactly the one that you want. Well, the more different parts there are for us to assemble from, the better off we are. And in my field, those parts look like this. Nature has given me on a silver platter a huge array of different parts. To me, these are beautiful. They're also highly functional. Remember, these are the objects that can convert one form of matter into another or store information. I've already mentioned the diversity of components that's important for innovation, and I've already mentioned the diversity of experiences when I described Angela Belcher's work. Accepting a prize more than 30 years ago, Steve Jobs famously said that it was really important to have a bag of experiences, that a young person needs to collect a bag of experiences, and not only have a bag of experiences, but it should be different from everybody else's experiences. Otherwise, you won't be innovative and you won't get a prize, is what he said in his inimitable fashion. But it's really true. Everybody wants a recipe, right? Young people are eager to come to you for a recipe for success, but really the recipe is to have different experiences and try to be risky, try to be innovative, and try different solutions to problems. Use this diversity. Now, the other thing that's important is a diversity of minds. So having these different experiences and using the minds that are available and offering them the potential to move forward is critical for the success of the innovation and technology evolution. And finally, there's the fuel, right? So we heard about funding. We have to invest in it. We have to provide the fuel for this innovation. And then we have to provide an environment where one can take risks, where the willingness to go out into the unknown is not cut off at the knees by the desire to work so incrementally and with such conservation. What we see in the biological world is that solutions to problems can come up from anywhere, and having that diversity of genetic material is critical for success. We need to provide an environment where that innovation can come forward. I like this cartoon. This is the way we shouldn't treat our students. Yet we do happen, in many cases, to treat our students much more like this cat. We have to allow them to go outside. So I want to conclude this short set of thoughts by saying we have this new era of synthetic biology, and I hope that life will continue to be a source of inspiration and not just exploitation, that we will be inspired. It's a new opportunity for inspiration, because this code of life, this product of 4 billion years, is incredibly rich. It's really wonderful, and it's something that we do not know how to write. But we are learning quickly, and I think the next 100 years we'll see that learning take off in directions that I have a very hard time making predictions about, other than it will be beautiful. And with evolution as our guide and our editor, I hope that the life we write will support our own and will be equally beautiful. And with that, I want to congratulate the National Academy on 50 years of contributions to this country and to the whole world, and I hope that the next 50 years will be even better than these. Thank you.
Thank you very much. Very inspiring. Frances, thank you very much. A very inspiring talk, and I think it gives us all a lot to think about. And you're attaching the evolution, the natural evolution. I'm not sure everyone here has thought about the same way you have, so thank you very much for that. That's really, really wonderful.